Hello and welcome to a new section in Algebra 1. This is section or Unit 7, and we're going to be talking about exponential functions. Okay, and specifically for section 1, we're going to talk about exponential growth functions. What I want to talk about first is exponent rules. Okay, so an exponent, let's just talk about what an exponent is real quick. So an exponent is the small number to the right of the small number to the top, number to the top, okay, that tells how many times you multiply your base by itself. That tells how many times you multiply a number by itself. Okay. So what we can do is, if we talk about our exponent rules, let's talk about what happens when we need to add our exponents. Okay. And so when we add our exponents, when we think about it, we have, say, like, let's just look at the number like 2 to the third times 2 to the fourth. Okay, and if I were to write this out, I would say 2 to the third, that means I'm taking 2 times 2 times 2. Okay, here's your exponent, here's your base. So the 3 tells you how many times you're going to multiply 2 by itself. So 1, 2, 3. Okay, so I have that. And then multiply that by 2 to the fourth. So 2 times 2 times 2 times 2. Okay, and so then the question is what happens when you have 2 to the third times 2 to the fourth? You have a total of how many 2's? That means that you're doing 2 to the seventh. Okay, so what we can say here is that if you had 2 to the third times 2 to the fourth, then really you're just adding your exponents. So really you can really just say 2 to the 3 plus 4 power, which gives you 2 to the seventh. Okay, and that's it. Okay, let's look at an example where you had, like, say, variables, where you have, like, say, like r squared times r to the third power. Okay. And what that would do is it would just give you r times r, okay, so you have 2 of them, times r times r times r, 3 of them, which means you'd have a total of r to the fifth. So really, if you don't have numbers, you could do the same thing with variables. Okay, if you have r squared times r cubed, then that's going to give you r to the 2 plus 3 power, which just gives you r to the fifth. Okay, so you get the same thing there. All right, let's talk about subtracting exponents. Okay, so subtracting exponents. All right, so let's think about something here. Let's think about, if you have, say, like, 4 to the sixth divided by 4 to the third power, then that would give you 4 times 4 times 4 times 4 times 4 times 4 divided by 4 times 4 times 4. Okay, so 3 of them. So what happens is you've got 6 of these. Okay, 4 to the 6th power means you're multiplying 4 by itself 6 times. 4 cubed means you're doing 4 by itself 3 times. Okay. Now, if you look at 4 divided by 4, those divide out to 1. And these divide out, and these divide out. And so you're just simply left with 4 to the third. Okay? So one way to think about it is, how do you use the numbers 6 and 3 to get 3? And the way you think about that is you subtract them. So if you do, 4 to the 6th over 4 cubed, then you're really just doing 4 to the 6 minus 3 power, which is going to just give you 4 cubed. Okay? And that's that. Okay, if you extend this idea to variables, okay, let's say you have x to the 7th divided by, say, x squared, then that's going to give you x times x times x times x times x times x times x, 1, 2, 3, 4, 5, 6, 7, all divided by x times x. So then x divided by x goes out, x divided by x, and you've got x to the 5th. Okay, so how do you use 7 and 2 to get 5 as a new exponent? Well, you just subtract them. So if you had x to the 7th over x squared, then really you're just taking x to the 7 minus 2 power, which gives you x to the 5th, and that's it. Okay, so there's those. Okay, so you've got to add exponents, you can subtract exponents. The other one you can do is you can multiply exponents. Okay, so if you multiply your exponents, okay, then you've got, let's say you've got, x cubed. Let's say you're going to do that, you're raising that to the 4th power, okay? And really what you're doing here is you're saying, okay, it means I've got x cubed times x cubed times x cubed times x cubed. Okay, and if you were to simplify that, then what you'd get, because now you're just multiplying them together, you're going to add your exponents, so you're going to get x to the 3 plus 3 plus 3 plus 3 power, plus 3 plus 3, which is going to give you x to the 12th. Okay, so the thing of it is that you've got to realize is that, you've got, how do you use 3 and 4 to get 12? Well, you multiply them. So if you have an exponent raised to another exponent, then you multiply. So if you had that rewritten out, you don't have to do the long way. You can just say, well, this is just going to be x to the 3 times 4 power, which is going to give us just x to the 12th. Okay? All right, let's talk quickly about 0, an exponent of 0. Okay? So let's take a look at something. Let's look at an example. Let's say I have x to the 3rd power divided by x to the 3rd power. Well, if you do this a long way, you're going to get x times x times x divided by x times x times x. Okay, so all of these end up dividing out, okay, and you're just going to get 1 over 1, which is equal to 1. Okay? So, and the thing that you have to realize is that, if you take something and divide it by itself, you're going to get the value of 1, okay? But if I apply the, subtraction rule to this, if I take x cubed over x cubed, that's really x to the 3 minus 3 power, which is going to give me x to the 0. Okay, so what you have to conclude here is that if you raise something to the 0 power, you always get 1. So I'm going to write this out, okay? Anything raised to the 0 power, anything raised to the 0 power is always 1. Is always 1, okay? Now the last one that we have, well, let's just go ahead and we'll talk about that. If the other one comes up, we'll get there, okay? So let's talk about this next problem here, talking about exponents in the real world. So what we have is a situation here where a microbiologist is studying a bacteria colony on a nutrient-rich petri dish. He observes the colonies on the dish for the next 3 hours. How can we model this growth? Okay, so what you have is at the 0 hour, you have 1 colony. Okay, after 1 hour, okay, you have 2 colonies. So you have doubled 1 to get 2. And then after 2 hours, you have 4, and 4 is doubled what you have from 2. And then after 3 hours, you have 8, so that's doubled. Okay, so each of these are doubled. All right, they're doubled. They keep getting multiplied by 2, doubled. So what we do is we model that using an exponential function. So this is what we call exponential growth. So exponential growth. Okay, and what you end up having here is this function, I'm going to call it f of x, is equal to 2 to the x. Okay, and the way you think about it is if you plug in, 2 to the 0 power is equal to 1. Okay, 2 to the first gives you 2. Okay, 2 squared is equal to 4. 2 cubed, 2 times 2 times 2 is going to give you 8. Okay, so when something gets doubled, okay, and these numbers are getting really big really fast, you have an exponential function, okay, and we model it like that. So let's take a look at what that function is, okay, and an exponential function is in the form of f of x is equal to a to the b to the x power, okay, and so the initial value that you have, and the initial value is when x equals 0, okay, that's your initial value. Base b, okay, where b cannot equal 1, is positive, okay? It is your rate of change, considered your rate of change in this factor, and it is called your growth factor when b is equal to 1, okay? The exponent is x, okay? And your domain on an exponential function is all real numbers, all right? So what you have, all right, and we're just going to kind of continue looking at that value of f of x is equal to 2 to the x power. And one of the things we have to think about is that when we plug negative numbers into this, okay, and I'll talk about, let me go over here, before we do anything, let's talk about negative exponents. Let me do that down over here. Okay, so hopefully we got some room. Okay, let's talk about negative exponents real quick. So a negative exponents. Okay, let me kind of introduce that real quick. What you end up having here is you have, let's just say you have, x to the third divided by x to the seventh. Okay. Now, if we were to do the subtraction model, and well, let's go ahead and just do it all out first. We've got x times x times x divided by x times x times x times x. So 1, 2, 3, 4, 5, 6, 7. Okay. When these divide out, x over x is 1, x over x is 1. You're left with 1 over x to the fourth power. Okay, now if we go through and we do, if we do that problem again, x cubed over x to the seventh, and we do x to the 3 minus 7 power, that means that we have x to the negative 4 power. Okay, so here's the crazy thing, is that when we did this, what we notice is that, when you do it the long way, you get 1 over x to the fourth. If you do it using the subtraction method, you get a negative exponent. So what we can conclude about this is that these two things are the same. Okay, and so if you have, say, the rule that you have would be if you have some number x to the negative n power, then that's equal to 1 over x to the nth power. All right, and so all you do is you move it to the denominator, 1 over that, whatever that is, and make it positive. And so when you plug in, and that's where you get these values, when you plug in a negative x value, you get these fractions, okay? And what happens is you get a graph that looks like this, okay? And here's that example of f of x is equal to 2 to the x power. Okay, when you plug in positive numbers for x, the y values get really, really, really big, okay? But when you plug in negative values for x, your y values are really, really, really small. So let's write that down, okay? So when you plug in, positive x values, so when you plug in positive x values, okay, the y values get huge. Y values get big fast, okay? But then, if you plug in, say, negative x values, okay, if you plug in negative x values, then the y values get infinitely small, get very small. Then the y values get very small. Okay? But they don't go negative. Okay? These stay positive. All right? So, and that's where we get this thing where you get a y value, when your range are going to be positive values for your y value. Okay? And that's the idea. All right, so now let's analyze a graph here. Okay, let's think about something here for a second. If we want to talk about the initial value, okay, we've got this exponential growth function, f of x is equal to 3 to the x. The initial value, remember, that's when x is equal to 0, okay? And that's going to be 1, okay? So your initial value is 1. Your base is a value of 3, okay? You have an asymptote, okay? And your asymptote, you know, you have a horizontal asymptote at y equals 0 for a standard exponential growth problem. Your asymptote is at the line y equals 0. Okay, your domain is all real numbers. Okay, always. And your range, you know, because you have a horizontal asymptote at y equals 0, your range is y values that are greater than 0. Okay, it's going to be positive y values. All right, so what you end up happening here, let's just go ahead and graph some of these. If I graph the point, you know, I start with 0, 1. Okay, that's always going to be on an exponential graph. So I have this point 0, 1. I have the point 1, 3. Okay, I have the point 2, 9. I have the point 3, 27. See how big these get? Okay, and then I also have the number negative 1, negative 1/3, negative 2, negative 1/9. These numbers get really, really, really small. Okay, and they just kind of shoots up like that. But it kind of hugs that line, and what happens is that these values will always get as infinitely close to the x-axis but won't ever touch, okay? And so let's kind of talk about that for a second. You know, that's your horizontal asymptote, okay? Your horizontal asymptote, okay, is the x-axis, okay? And what that means, an asymptote is an imaginary line, okay? So over here I'm going to say this is an imaginary line that the graph will not cross. That the graph will not cross. Okay, so it will get as infinitely close to that line, but it won't touch. Okay? All right, so let's talk about exponential rates of change and linear rates of change. Okay? And the difference is that when you have an exponential functions have a multiplicative rate of change, okay, means that every time you do this, you're multiplying by 5. Every one of these, you know, from this step to this step, you're multiplying by 5. This step to this step, you multiply by 5, okay, you multiply by 5. Here you multiply by 5, all right? And then here, you know, the difference between that and a linear rate of change means that you add 5. You have an additive rate of change, okay, which means that you're going to add 5 to each of these, okay? So first of all right, let's kind of talk about what that means, okay? And exponential functions have a multiplicative rate of change. Each y value is 5 times larger than the previous one for the consecutive input values. So notice how when you just keep multiplying this by 5, when you multiply, this graph shoots up, okay, and it has a curve to it. Okay, but when you have a linear rate of change, you keep adding 5, and so you have a constant rate of change. It goes up at the same rate, okay? So that's what's going on. All right, let's talk about identifying exponential rates of change. Okay, so what we want to do is we want to take a graph or take a bunch of, or take points on that graph, and we want to determine what exactly our rate of change is. Okay, so here's what we have. Okay, let's make a table here, and I'm going to do it out over here, and I'm going to do a horizontal one. Okay, here's my x value, here's my y value. If I plug in negative 1, okay, I get 2/3. Okay, if I plug in 0, okay, I get 1. Okay, if I plug in 1, I get 3 halves. If I plug in 2, I get 9 fourths. Okay, if I plug in 3, that's going to give me 27 eighths. Okay, if I plug in 4 for x, I get 81 sixteenths. Now, what I know is this. I'm going to put this over 1 real quick. Okay, and I'm just going to kind of look at the positive values, all right? The way that I can tell and write my function, okay, is to think of that formula a times b to the x, okay? Obviously, these numbers are getting bigger, so we have exponential growth, okay? So a is our initial value. So when we think about that, our initial value, when I plug in 0 for x, I get 1 as a value. So I'm going to come over here and I'm going to say, all right, well, if I plug in my initial value, a, is 1, and I get that from this number here, okay? To find out what my b value is, I need to look at where x is equal to 1, and that's my b value. So b, in this case, is equal to 3 halves, okay? So what I end up having here is I can write this function, f of x is equal to 3 halves that quantity to the x power. Okay, and the way I can kind of also think about that is that, you know, if I plug in, say, if I do 3 halves quantity squared, if I plug in 2 for x, I should get 9 fourths. And if you look, notice how what I'm doing is I'm taking 3 squared over 2 squared. Okay, and that's going to give me 9 over 4. Okay, same thing if I plug in 3. If I do 3 halves quantity cubed, all right, then I'm going to get 3 cubed over 2 cubed. 3 times 3 times 3 is 27, and then 2 cubed is 8. Okay, and we get that number here. But the trick is to look at when x is 0 and when x is 1. That tells you what your a value is and what your b value is. And then you can just write your function. Okay, so not too bad. All right, so exponential growth functions, okay, we always have this part here where a times b to the x, okay, the initial value is a, and it should be greater than 0, okay? The base b is greater than 1 if we have a growth function, okay? We'll look at other parts where if we don't have that, it'll look a little bit different, okay? Okay, let's take a look at this, all right? And what this says is scientists are studying a specific group of 6 penguins. The population of penguins increases at a rate of approximately 24.5% per year. What function can be used to find the number of penguins in the group after X years? Okay, so this is a little bit interesting, okay? The way I get this, all right, and it's not as easy as, you know, the previous one, but what I know is that this is going to needs to be of the form f of x is equal to a times b to the x power, okay? Now, when x is 0, okay, then what happens is I have to look at that and say, all right, well, how can I go from, when x is 0, what's the y value? Okay, and that's my value for a. So in this case, I know what a is. A is equal to 6. The question is, how do you find this b value? Okay, and so what you have to do is kind of think about this for a second. And let me kind of write out my values for x and values for y. Okay, if I plug in 0 for x, I get 6. If I plug in 1 for x, I get 7.47. Okay, if I plug in 2, I'm going to get 9.3002. Okay, now what I'm going to do is kind of unique here. Okay, remember how each of these is being multiplied by a number. Okay, so what I'm going to do is I'm going to do some division to find out what my constant rate of change, or what my multiplicative rate of change is. And so what I can do is you have to use division. You know, when you did a linear rate of change, you use like addition and subtraction. But what I want to do is I want to take the number 7.47 and I'm going to divide that by 6. And when I put that in the calculator, I'm going to get the value of 1.245. Okay? Now, I'm going to do the same thing over here. I'm going to take the number 9.3002 and divide that by 7.47. And the crazy thing is that I get 1.245. Okay, I get the same thing here and here when I take these numbers and divide it by the previous number. Okay, so that is my value for B. Okay, this is how I get B. This is my value for B. So then B is equal to 1.245. All right, and so then I just write my function and say f of x is equal to 6 times the quantity, 1.245, all raised to the x power. Okay, so, make sure that you watch this video and see how I get these numbers, okay, and write down some of these steps, okay? Some of them are pretty easy to do, some are not as easy. Okay, I hope you enjoyed this video. I had a lot of fun making it. We'll see you soon. Bye!